Oh, yeah, sure. Okay. Yeah. So it's a pleasure to be here, and we have two talks in this session, both half an hour each, and both speakers have 25 minutes to talk, and then 5 minutes of discussion. Our first speaker is Subhendra Mohanty from Physical Research Lab, Ahmedabad. He'll tell us about ultralight dark matter. Over to you, Subhendra.
Right. Thank you, Basu. So let me start by thanking the organizers for giving me this opportunity. And this is a subject that I actually want to talk. I've been doing this. I mean, the fact that your standard paradigm of cold dark matter hasn't yielded any experimental positive results from either laboratory for the direct detection or indirect detection or at LHC. So people are looking at other uh, models of dark matter than the standard cold dark matter. So let me start by saying, why do we need dark matter? So we now, this is the end of the conference. I'm sure you've seen all this before. So we need this dark matter of any kind for explaining the rotation curve, for explaining the fluctuations of the CMB spectrum. You also have the large scale structure where you have a 2D survey of galaxy with the, when you measure the redshift, you get the 3D survey. And then you have this bullet cluster where two clusters have passed through each other, and there is offset between the visible matter which have scattered and the dark matter which went unscattered, which was inferred from the lensing. So all these point towards they need a dark matter to explain all this. You can't do without dark matter. But what is the particle nature of dark matter is, of course, not clear yet. Now, there is not everything is fine with the cosmological or astrophysical evidence for dark matter, or the cold dark matter rather. So here there is a compilation by Max Tegmark that at different length scales, what is the fluctuations and where you see them. So you see them either in cosmic microwave background at 1000 megaparsec, then clusters at 1 megaparsec, and then slowly towards galaxies. So the galaxies are at about 100 kiloparsec. So over this wide range of parameter of your length scale, you have to explain the perturbation, density perturbations, fluctuations, which has to match observations. And there are some evidence that the small scale structure does not quite match the large scale, or rather the lambda CDM, which is okay for large scale structures, is not quite matching structure at the small scale. So let me explain what that means. So if you go inside the galaxy, so here is the, you can, your simulations of cold dark matter, by cold dark matter I mean particles of 10 GeV mass or above, and whose scattering cross section is lower than the weak interaction cross section, or about lower than or equal to the weak interaction cross section. So gravitationally, I mean in astrophysical, they do not scatter at all. So the cold dark matter simulations predict a profile which can be approximated by this analytical formula called the NFW profile, which I've shown here. So here SRS is some sort of the core radius of the galaxy, and R is the radius. So this tells you what is the dark matter profile over R. And if you expand this at R smaller than RS, you see that your profile falls off at R to the -1. So that gives you a particular, this particular profile when fitted with the rotation curve of the galaxies doesn't quite match. So this is what I've shown in the left side in the, so this is taken from dwarf galaxy survey, which is like they measure the rotation curve on the inner part of inner 1/3 kiloparsec of 0.3 kiloparsec of seven dwarf galaxies. And what they found was that the rho, if you parameterize rho as rho going to as r to the alpha, then your NFW says that you should have alpha going to the minus equal to -1, whereas what observations tell you is alpha is minus 0.3 plus minus 0.07. So basically, there is a flattening of the density towards the center, whereas NFW or the cold dark matter simulations predict that the profile actually spikes towards the in the core. So this Cuspy core, which is predicted by NFW, is not seen in observations of rotation curves in the inner part of inner, like less than 0.3 kiloparsec of your rotation curve, and this is tells you that maybe there is something more in the the nature of dark matter than just cold dark matter. And one of the popular models is self-interacting dark matter. So what that tells you is that that when the dark matter falls towards the core, then there is a scattering. It scatters with itself, and so it prevents that scattering of the dark matter, prevents a gathering at the core. But that's not the subject of my talk. I will be talking about another this thing which is which solves this problem, which will be the ultra light dark matter. I'll get to that. Another problem which may or may not be there, but it has been touted as a problem for CDM, is that you in CDM simulations you predict many more dwarf galaxies around our Milky Way than which is shown on the left, and then what are the handful of galaxies shown which are the dwarf galaxies which we see, which are shown on the right, which are seen in the around the Milky Way. So but this is not it's not clear that it's because we haven't observational bias that we have not really seen faint galaxies, or whether there are actually no faint galaxies. For instance, there is this of faint in the lower panel of faint galaxies which are in red, and the blue galaxies are the very luminous galaxies which are observed. So these faint galaxies have shown up in the SDSS survey, and you can see that there is this the mass on the y-axis and distribution of luminosity. So what this tells you is that you can have 10 to the 7 mass galaxies which are actually very low ultra low luminosity. So they are not much scatter in mass, which means basically the dark matter forms the galaxy, whereas some galaxies have star formation, some don't have a star formation. So you may have your dark your dwarf galaxies formed by your CDM, but they may not be star formation. So here the data is not exactly, not yet settled whether there are missing dwarf satellites or not. But this was one of the problems which was touted as a lacuna for cold dark matter. So I'll get to the topic of my talk, which is ultra light dark matter, which also goes by the name of fuzzy dark matter. So what and so this famous papers, very well cited, Hui, Ostriger, Treman, Witten, and Gruzino. And so what here the paradigm of dark matter is very, very different. So here what they say is that they first try to solve the core cusp problem, that if you have a cold heavy particle, it will cluster in the center and give you a spike. Whereas if you have an ultra light particle whose de Broglie wavelength is of the size of your inner core of the galaxy, like if you kiloparsec, or the size of your dwarf galaxy basically, then you cannot collapse that particle towards the center at the inner 1/3 kiloparsec distance. The same reason that you cannot collapse an atom, the electrons in an atom, because the uncertainty principle tells you that you cannot do that. Okay. You cannot localize that particle. So by having this de Broglie wavelength over the size of a galaxy, you prevent a spiking of at the center. You can derive the density perturbations not by solving the standard perturbation equation, Einstein's theory, the classical equation gives you the Jeans mass, but you calculate the density perturbations using the Schrodinger equation. So using the Schrodinger equation, you write the equation for the probability and density, and from that you get the density perturbations equation. Now this density perturbation equation will give you in detail what I was telling you, that you cannot form structures smaller than, you cannot localize a particle to smaller than a third of a kiloparsec. You can also, solving this equation, get what is the Jeans mass. So you have the Jeans wavelength, where you in the if your kj at smaller scales, you will have a growing solution. If your if you concentrate the mass smaller than the kj inverse, then you'll have a growing solution. So basically this tells you what is the smallest size structures you can form. And from that you can derive the smallest size mass that can form. So this gives you 10 to the 7 mass, solar mass, for m, which is of the same 10 to the minus 22 eV. So basically this 10 to the 22 eV mass of this fuzzy dark matter comes out from two different things. So now this solves the galaxy, and this too big to fail problem is another way of stating this, not seeing the dwarf galaxy, in the sense that the CDM also predicts larger galaxies which are too big to not have star formation, so that they are ultra faint, and those are also not seen. So that is called the too big to fail problem, and these things are solved by this fuzzy dark matter, because you cannot form structures smaller than 10 to the 7 solar masses, which is the size of some dark galaxies. And for these, the common theme is that your mass should be 10 to the minus 22 eV. Okay, so that tells you that you are dealing with an ultralight particle. Okay. Now you can also calculate the power spectrum, and you can match it with the observations from CMB and the large scale structure in detail. So this is done by this paper, Hozerek et al. From in 2015. So you'll see these constraints from large scale structures. And so basically what the ultralight dark matter does is erase structure at small length scales. So there is, in the green, you'll see the lambda CDM, and the power at large K is goes down as you reduce the mass of this dark matter, and you assume that the whole dark matter is your ultralight dark matter. So if you want to erase power at small scale, that you prevent your dwarf galaxies and small galaxies, then this is one way to do it. Okay. Now we go to what's the cosmological evidence of this ultralight dark matter. So this was at galactic scales. It solves your core cusp problem. It also tells you that you cannot have dwarf galaxies, small galaxies. Now we go to what is that happens at the cosmological scale. So here the calculation is similar to what you have in AXIONS. So the only difference is that in AXIONS, so for instance, if your fuzzy dark matter is a pseudo-Nambu-Goldstone boson which has a shift symmetry, then you can write generically the potential as some mass parameter to the fore and a cosine A by F, so that you have this shift symmetry. A goes to 2 pi A plus 2 pi F. So you have two different scales, mu and F. And if you expand this cosine and take the coefficient of the A square term, that gives you the mass square of the dark matter. So that mass square is mu to the 4 divided by A square. That's the mass square of the dark matter. So the difference between the standard the standard axions, and so and this is that in axion models, even the invisible axion models, you have some relation between M and A. Here there is this M and A are independent parameters. Secondly, for QCD axions, there is no mass till your QCD phase transition, but here this mass is always there. So if you treat this M and A as independent parameters, we have already pinned down M from the galaxy and structure formation. So we have to find out what is F and whether that gives you a reasonable relic density. So you can write down the equation of motion for this A using this potential, and solving this equation of motion. So this is the equation of motion written again. So when your mass of the particle is smaller than, when your Hubble expansion rate falls smaller than your mass of the particle, then you just have a harmonic oscillator type of equation. So A double dot is M square sine A. The H term is subdominant. And this, for a M equal to 10 to the minus 22 eV particle, happens at T, temperature of 500 eV. So at the time of BBN, which is MeV or so, there is no, the radiation is the dominant one. This is a subdominant oscillation going on in the background. This starts dominating only at 500 eV. So this is a late appearance of dark matter. It appears only at T500. At that point on, you see this coherent oscillation of dark matter, which is similar to what's the axion thing. Now, if you work out, you can take the density of the axions at this time when the Hubble, there is the mass equal to Hubble, and then calculate the dilution from that time to now. And if you take this density of dark matter to be the present relic density, then this gives you an equation for F. And that gives you that if your M is 10 to the minus 22 electron volt, then your F is 10 to the 17 GeV. So this last line gives you a sort of a parameter. So this tells you that this is some sort of a string axion or something little more than the gut scale. So, but it is not a crazy number for F. So you have now a paradigm where you have a dark matter whose mass is 10 to the minus 22 eV and whose coupling with other particles is 10 to the 17 GeV.
Subhendra,
yeah.
We lost you for like a minute.
Yeah.
I think we lost your connection for a minute. We lost your connection for a minute or so. So could you start by saying, you said that F was 10 to the 17 GeV and it's not a crazy number.
Yeah.
After that, what did you say?
So I said that F is 10 to the 17 GeV, and this is something like your string scale between your gut scale and the string scale. So this is not a crazy number in that sense, and it's not like 10 to the 25 GeV, which is beyond what, so far we haven't gone beyond Planck scale for any kind of parameter for your any particle physics parameter. So this is well within Planck scale. So that's what I meant by saying that it's not a crazy number. And there are models from maybe string theory which tells you that maybe you can have the string axions which will give you this fuzzy dark matter. Okay. So now we try to investigate that if something has a coupling of 10 to the 17 GeV and mass of 10 to the minus 22 eV, where do you see it? So I've already told you that there are, of course, constraints from CMB and large scale structure, because this was constructed to solve those problems. But apart from them, are there any? So that's what my rest of the talk will be. So I'll be talking about this ultralight dark matter detection from binary pulsar timings. So basically, my model of this dark matter will be that these particles, well, they were constructed to be axion-like particles, but they can also be vector particles. So if you have a long-range gauge boson, a very light gauge boson, then the zero component, the vector component can be zero. And for instance, mu, the A0, which can be non-zero, and the A0 can oscillate and give you this ultralight dark matter. So the zeroth component of your vector, 4-vector dark matter, which can be a gauge boson, or your ultralight axion-like particle, they can both serve as this ultralight dark matter, and my talk will be how to find it from other things. So in particular from binary pulsar timings. So here you have a picture of a pulsar and a binary pulsar. So basically in a binary pulsar, you see at least one of the binaries, and then from the motion of that pulsar that you observe, you figure out that it is a part of a binary. And one of the earliest observations of very precise timings, and these are monitored the pulsar time period, the orbital time, not the rotation time, the orbital time, when these two pulsars are about a astronomical unit apart. That's the typical distance of binary pulsars. The orbital time period of those pulsars is about 8 hours. And I'll tell you why that number falls nicely in this ballpark of the dark matter. So this orbital period of this binary pulsar has been monitored over the years. So some pulsars have been observed for about 20 years or more. And then and one sees that the orbital period of the time of the pulsar falls, which means that they are losing energy and they are radiating into something else. And the first thing, of course, which was discovered from this binary pulsar observation was that they radiate gravitational waves. So this was this Hulse-Taylor binary, and this is a plot of this time period over the years. So you can see from 1975 to 2005, there is a loss in the time period, and that follows the prediction of GR that they are losing energy by gravitational wave radiation. So going to the formula for this gravitational wave radiation, this was derived by analytical form of this was derived by Peters and Mathews. Now this used what is the dipole, the quadrupole oscillation formula of classical relativity, that you calculate the quadrupole moment of that binary pulsar, and you see the time period, the triple derivative of that, and the square of that will give you the d by dt. So that's a classical formula. It's a very complicated formula, especially. So this depends upon omega, the time period, the masses, the A, the semi-major axis, and E, the eccentricity. Now it's very difficult to, analytically it's difficult to derive this formula, but this especially if you have this eccentricity, but this eccentricity factor actually is very important. This calculation, this eccentricity for typical binary pulsars is a factor 10. So you cannot drop it and do simple calculation, a simplified estimation, because this is a factor 10 and you cannot do precise matching with the observation with that kind of formula. Now, as I said, this omega of 8 hours, if you convert that into energy scale, that is 10 to the minus 19 eV, okay, which means that these compact binaries, they have a frequency of 10 to the minus 19 eV, which means that they can not only, apart from radiating massless particles like gravitons, they can also radiate ultralight particles whose masses are less than 10 to the minus 19 eV. Now, though that is the ballpark of this fuzzy dark matter, so this would be a good place if there is fuzzy dark matter which couples to normal matter. You can see if they are being emitted. So they are being emitted not by individual stars, but by the whole binary as a whole. So this binary star acts like an antenna, and it can radiate scalar particles. It can also radiate vector particles. So that's what I'll. So that's what we derived formulas for that.
Subhendra, sorry, just to interrupt. You have another 5 minutes or so, including questions. So maybe you want to
okay.
Well.
Okay, yeah. I'll hurry up then. So basically what we did was we calculated the first the trial run. We calculated the Mathew formula for gravitational wave radiation using a Feynman diagram method. So you just have a classical current, which is just the binary pulsar, and it radiates one graviton. And you do the calculation like you normally would. And in the last line, so we went through these steps. And this was the publication which I showed, 1996 publication. So we calculated the Matthew's formula. So which means that this method of this Feynman diagram technique works well with the kind of thing we are familiar with, and this analytically easier to do this. So we got the exact formula which for gravitational wave radiation. Then we did the same thing. So this gravitational wave radiation then gives you the energy loss, and that is what matches with the standard expression the plot of which I showed. We also did in the same paper that if you have a scalar coupling to quarks and you have a very light scalar, then what will be the coupling constant? Of course, at that time we did not have this fuzzy dark matter paradigm, so this was just a game. But the technology of calculating this was worked out, and the energy loss formula was derived, including the eccentricity factor. But now this was recently we applied this to this fuzzy dark matter, that if you have, so this was worked out by Hook and Huang, that if you have a neutron star which couples to this axion-like fuzzy dark matter immersed in this oscillating fuzzy dark matter, then inside the star, if you match the boundary condition, you have a long range force, and from the binary, the long range force particles will be emitted because of the oscillations. So this basically, there is a charge, effective charge, which depends upon Fa, and we applied that scalar formula with this effective charge, and we found that this F is smaller than 10 to the, for these very observations, less than 10 to the 11, 10 to the 16, 10 to the 11, so on. So it's clear that 10 to the 17 is ruled out, which means that if you have fuzzy dark matter with 1 by F coupling, those do not couple to quarks. They have to couple to either leptons or nothing. So this is a kind of a strange kind of fuzzy dark matter, that 1 by F universal coupling is forbidden for quark, even with F 10 to the 17. Okay. So the other model for fuzzy dark matter is the vector bosons. There are these three, you can couple these three kinds of charges in an anomaly free way in the standard model, and you can have a model of vector dark matter. They are, if they couple to electrons, then electrons in sun or earth can act as a source, and they can influence neutrino oscillation. So this was done by Joshipura and myself in 2004. But if you have something at L mu minus L tau, then from normal astrophysical bodies, you do not expect a long range force of L mu which couples to L mu or L tau, the mu1 or tau quantum number. However, it was observed recently that this, this is known actually, but they brought it up to attention, that in neutron stars, there is a substantial number of muons. So a neutron star has 10 to the 57 neutrons, but it has 10 to the 55 muons. Okay. Basically, the muon decay is beta block. So muons stay there in the neutron star without decaying. And then if you have a vector force, then it also should radiate in binary pulsar. So we did a fresh calculation for what is the radiation rate for vector particles. So this is like the Larmor formula, but with eccentricity put in. So this was done by Podar, Jana, and myself in this paper, recent paper. And this was compared with observations, and we put some bounds on this mass and coupling of this from the pulsar observations. Now, one interesting observation from Dror, Laha, is that normally I'm discussing this orbital binaries in a steady state, but when you have an inspiraling binary at like in the last 15 minutes, then they are much closer together, and when they radiate, they also, you are seeing that radiation also in the signal at LIGO. So if you have extra radiation, then it will affect the LIGO signal. So they did this analysis that if you have extra source of radiation, what will be seen in LIGO, and they established very good bounds on the G and MZ from the gravitational wave signal. And I see from the timetable that Laha is speaking this conference, so I'll not say more. I'll let him continue. So the paradigm of this is there's a advertisement for my book which is coming up. So what's in this book is one of the chapters. What I've tried to derive is that you have this effective field theory of your current, classical current, which is coupling to a spin 0, spin 1, spin 2 particles like the graviton. And you can do these calculations of your binary radiation or even your gravitational waves using Feynman diagram technique. So something that we are familiar, particle physicists are familiar with. They can calculate signals for this other astrophysical type of signals using Feynman diagram techniques. So that's something that can be even. So this is now done at the tree level, but in the loop corrections, etc., they can be refined even further. Okay. So that is all I have to say. Thank you very much.
Okay, thank you, Subhendra. Let's all thank Subhendra for fighting through his cold and also congratulate him for this wonderful book. We are all looking forward to it. We are out of time, but if there is a quick question, we could take it. Yeah, there's a comment from Subinoy. Yeah. Go ahead.
Hi, Subhendra. This is a nice talk. So just to let you know that from our AXION talks by David Mars, so recently there is a paper by Hiranya Perry's group. It has been ruled out that the mass range of ultralight axion 10 to the power minus 19. So it has to be greater than that. So this 10 to the power minus 21, 22 is almost gone. So only a half fraction of ULA is allowed. But I see that 10 to the power minus 19 can also be detected from in your range.
Okay, thank you. I'll look it up. I haven't seen the
Maybe I'll send you the reference. So Shiv from RRI is redoing the Lyman alpha bound on that, but pretty much similar bound. He's also.
Oh, I see. Okay, thanks.
Yeah.
Okay, I think we should move on because we have another talk. Let's thank Subhendra one more time and welcome